这上面有格式应该不会变的。马上开始了，下回您再找一点。开始，等一下，给你一下 U 盘。
Good morning, ladies and gentlemen. Welcome back. Please be seated. So let's start the first session this morning. And the first speaker is from Italy, LNS, Professor Cirone. So he will give us a talk about the last results on BB11 used with low and high repetition rate lasers and associated diagnostics.
This one. Folder for moving the slide. Can I use this? For this.
7 minutes. I have 30 minutes for total and for the mouse. 25 minutes.
To come back. This is the laser. No, to come back. Okay. This work.
Okay, thank you very much. Hi to everyone. Thank you for the invitation to the committee organizing chair. And okay, I'm Pablo. I come from Italy, from Italian Institute for Nuclear Physics. So this laser not to work. I will use it. Okay, Italian Institute for Nuclear Physics. And I will discuss, I changed a little bit the title of the talk. I will discuss on our last activity on Proton-Boron 11 indeed, and the future perspective that we are affording at INFN. And in Italy in general, I would say this is the big collaboration that includes most of the people who we are in, which we collaborate. So we are here in Istituto Nazionale di Fisica Nucleare in Italy. These are the guys working on this topic. Then there are people from University of Catania, from Enea institution in Italy, Polytechnic in Turin, collaborator from US, from LI Line, from the University of Tor Vergata, University of Bordeaux, and the Institute of Plasma Physics, and probably I forgot someone that worked in this topic during the last 10 years. So my talk, I will show you the activity that we carried out at the Pulse facility in Prague. So some results on thick and thin boron target that we had on proton boron. Then I will speak on our fusion project. This fusion project was a project that was funded by INFN in the year 2023-26, where we had some results and data are ongoing. And then I want to tell you something on the new project that we are launching on the measurement and the development of algorithm models for the stopping power, ion stopping power in plasma, and how we will do this inside our new laser facility that we are developing at our institute, that is the ILUCE facility. You already saw the talk from Dr. Alonso on the high repetition rates. They collaborate with us, so you already saw this talk, and some possible perspective that Dr. Harjmand presented during the first day. So I will skip this part on high repetition rate work that we do together with them, and on the possibility to use discharging borated medium for stopping power measurements. So it's almost 10 years, perhaps more, that we work at the NFN with inside with this laser pulse. So the results that I will show you are connected to this kind of laser, that is an iodine gas laser with a quite long pulse, you know, and an energy that a working energy that is around 400 to 600 joule in each shot. So the nominal intensity of this laser is something around 10 to 15, 10 to 16. Perhaps during the last experiment we get more, 10 to 17, perhaps 10 to 18, because we understood that the focus spot was smaller than the nominal one. By the way, this is a low repetition rate laser, you know, but it's able to give us the energy sufficient to study our target and our diagnostic, etc. So the work started in 2016 with the different campaign that we have. Then now we are working a lot inside this pro bono cost action that will end this year. In the meantime, the fusion project started. So there were other campaigns, experimental campaign, 2024, 2025, and I will show you fast some results. So these are some results from the experiment during 2016 and 2017. We had this campaign using thick MV targets. So we observed alpha energy, post-accelerated alpha energy with a very high yield, 10 to 11 alpha per shot. These are some results from time of flight, detector that we use, CA39 and Thomson spectrometer. There the setup is, the setup quite simple, laser, and we studied that in the back direction, as expected, the laser, the emission of the alpha from this NB target. And you know very well these results that we published in 2022 paper. Yes, so these results that we get during this campaign. Well, then on the same experiment we do. This experiment was performed with a thick target. During the same campaign, the next year, we performed in the quite similar configuration and similar target, another experiment, but using a thin target. So same kind of target, but in thin target. So the laser in this case, the target was completely destroyed. We put the detectors all around, still in this case, we observed a post-acceleration mechanism on the backward direction still. And we studied in this case the proton emission, the alpha emission in this direction, so in the forward direction, not in backward, with this number of alpha that were recorded by our diagnostic. Then these are the two first results that we get that are already published. Then in 2023 there was this project. It was a very big collaboration, the fusion project, where we started to perform tests on new material and a new detector. I will show you some new development that we had in the field of proton boron in this project. So this project was focused on developing new target. Develop new diagnostic and combining different diagnostic together with other colleagues. We had two campaigns at the Pulse facility, and inside connected to this we have also high repetition rate measurement that were discussed on the first day by Dr. Alonso, as I already said. So for this experiment, we used the completely, the goal of this experiment was to measure in the same shot both the in-target emission of particle and in the picture catcher scheme. So basically, we develop such kind of target holder. So we have the primary target, so the laser interacts with the primary target. Then you have an emission of alpha and protons in this direction, in the backward direction, and particle reach here, and here there is the secondary target. So during the same shot, we had the possibility to measure the alpha that are produced in target, in the primary target, and the alpha that are produced here in the secondary target. Then there are some diagnostics, CL39, and all diagnostic that is around. So this is the holder inside the vacuum chamber. So laser comes from this direction. This is the primary target. And then there is the emission of particle in this direction. The target is tilted to 25 degrees. So this is the normal direction to the target, that is this one. And then here all around there are different diagnostics. We were able to test different targets. So we have different target with the borated target developed at the University of Catania. Foam target developed in the collaboration with Enea and the Polytechnic of Milan Polytechnic. Target with ammonia boron coming from RAL, and probably tomorrow Dr. Turco will say something. Electrospin fibers with boron developed at the University of Salerno and Salento, sorry, in Italy, and the target coming also from the ELIBE in line with their nanoparticle studies. So we had the two campaigns. The first one we started to see which was the best configuration, and then in 2025 we had a consolidation campaign. And we are now analyzing the results. Indeed, we are starting to publish the results that we had. So basically, we use a complex system of diagnostic. We have CL39 coupled with the differential aluminum filter in order to make the diagnostic of alpha. We connected this to the Thomson spectrometer. In this case, we used one Thomson spectrometer. Sometimes we use two Thomson spectrometer. We have and develop a diamond and silicon carbide detector. I will tell something on silicon carbide in particular to have online time resolved ion spectra, and we measure the activation using different germanium detectors. Okay, this is typically we use a CL39 with 6 filters, and we are able to study the different regions and to try to disentangle the information from alpha and from proton and different ions. Of course, we used also interferometric technique and electrospectrometer technique in order to study the plasma that is generated. Inside the project, we developed a nice sensitive Thomson spectrometer with an increased acceptance. So this spectrometer working very well, very close to the target. So the resolution of this object is very high. We are able to put this very, very close to the target in order to study the plasma. This was developed by the group of Enea in Italy inside the project. It was tested. And we developed a completely new approach using a time-of-flight detector in a matrix. So this is a matrix of diamond detector. These diamond detectors are placed looking to the same angles. There are different filters. So these are CVD, chemical vapor deposition diamonds that are mounted in a flange, connected with different filters. And we are able to distinguish in the same shot to make a spectroscopy using different filters indeed. And results are published in this work, recently published in this paper, recently published. Silicon carbide, there is a very important ongoing work on the silicon carbide. We developed, as I told you, diamond detector with the University of Tor Vergata and silicon carbide using the competence and work of the ST Microelectronics company that collaborate with us in this work. These are two kinds of different detectors produced by them, and we use this detector to monitor the beam, and these are some shots that we get. Now I will comment that we get during these experiments. So in particular, these are the results. I mean, I try to make a summary of the results that we get in the campaign of 2025 campaign. We registered one of the highest proton energy at pulse. So we registered on the backward direction up to 5 MeV, but during the last experiment, we get up to 6 MeV. And we are analyzing this data, so I don't want to show something that is not sure. But by the way, we had the evidence of protons up to 4 MeV, 4.5 MeV during this campaign. Also at very large angles, because we are able to perform some angular distribution of our detector. This is the example of, this is a Thomson parabola at 0 degree, and at another angle, this is the parabola, the Thomson parabola from Enea. So you see there are beams up to 5 MeV, more than 5 MeV on the backward direction, normal direction to the target. Very high proton flux, up to 10 to 12, 10 to 13 protons. These are protons per steradiant. So this allows us to basically activate the secondary target, and we studied the beryllium-7 decay. So basically, we were able to perform using the reaction of proton on boron 10 and studied the decay of beryllium-7. We were able to measure the number of alpha particles that were produced in the picture capture, in the secondary target. So we estimated, in this case, an alpha yield in the picture catcher scheme up to 10 to 5 alpha per steradiant. And this was good because we had two completely different diagnostics able to measure the alpha particle. And now we are evaluating the number of alpha particles inside the target, and the number is something around 10 to 8 alpha per shot. So this means that in the same shot, in the same series of shots, we were able to make a measure of alpha from the primary target, and so in the in-target scheme, but in the same target, we also evaluated the alpha in the picture catcher scheme during the same target. So this is something important for us. One of the goals of this experiment was focused on this, to try to distinguish the contribution by the two channel, let's say channel of this reaction. So these are CL39 registered for one filter, and these are electrospectral interpreters with red. Okay, so I told you this is results from different target. There are two different target, reference and boron target. We studied the angular distribution of, in this case, of protons, and you see we had the energy up to 5.1 MeV in this specific campaign with these flux protons and also protons around. And the results of these works is, I think, will be submitted within this month or next month maximum. An important point is that we use Fluka and Jean-Fort Monte Carlo simulation to evaluate the backscattering from the secondary target, backscattering of proton and carbon and eventually alpha that are generated. So basically, we have a Monte Carlo suite. I don't want to tell you the details. A Monte Carlo suite able to simulate particles. So we use Fluka and Jean-Fort both to simulate the number of particles that are generated, the number of alpha that are generated by the reaction, and the backscattering, and for subtracting the background in the detector, the background coming from the backscattered ions. And this indeed is the comparison between the Fluka simulation and so these are, the comparison of the alpha that we get using the Fluka simulation and the measured one. So we get a very good agreement when you simulate everything and we put the correct models inside the simulation. We were able to, corroborate our data, our alpha produced in the catcher using Monte Carlo simulation. Well, now which are the ongoing activity that we are doing after this long experience that we had at target? We are doing, so we work on this fusion project, I told you, where we developed a lot of target, a lot of diagnostic. We performed a lot of measurements, activation. We established CA39 and Monte Carlo cross-check. So one of the limits that we still have in our work, this is something that is also of interest inside the NFN, is the measurements of the ion and alpha stopping power in a plasma. That is a point that is important, as we know very well. And this measurement of the stopping power was the starting point from this new project, PSP, that is the plasma stopping power that we are launched at INFN. So we are asking, basically we submitted the proposal, and this work is done together exactly with the INFN. There is also some let's say, talk with the GEM4 collaboration and with the Hyperplus community to which we belong. And this project is also, performed together with the Enea. Dr. Fabrizio Consoli is the spokesperson with me of this project. So what do we want to do here? What do we want to do in this framework? We want to measure the ion stopping power in medium, so something between 10 to 17, 10 to 19 electron per centimeter cube medium density plasma, and in warm dense matter plasma. And we will use this to, validate, to make a benchmark, experimental benchmark of the first model for ion stopping power that we are inserting in the GEM4 simulation, so GEM4 Monte Carlo toolkit. We develop with GEM4, we develop GEM4, we are GEM4 developer, and we are proposing already since 2 years inside the GEM4 collaboration, the development of some G4 plasma class to give to GEM4 the possibility to simulate some plasma state, so models and material, plasma material inside GEM4. So the experiments will be carried out at Eli Alps inside a project that was proposed by Professor Luca Volpe at Eli Alps in Hungary, and at our laboratory at NFN using a plasma discharge, a plasma generated in an electrical discharge that was discussed by Dr. Osman on the first day. So we hope that fully we will release the first model inside GEM4. We are working on this topic. There are already 2 papers published. One is will be published very, very soon. So which is the methodology that we will use in these 2 experiments? We will perform an experiment at the Eli Alps. This experiment will last 3 years. So we will work in 2027, 2028, and 2029. So at Eli Alps, basically, we will take the main laser beam that will be a 9 joule beam. So there will be a laser beam that is split in 2. One is the main beam that will be bring to this target. So protons are accelerated by TNSA here. Then we develop an energy selector able to select in an isochronous way very short bandwidth of protons. So the duration of these protons is something of the order of 10 picosecond here. So proton exit here are collimated, and in the meantime, the second laser with the correct delay, the second laser will reach the target where we will perform the plasma. And in the picosecond scale after the interaction of this laser, this proton will interact with this plasma in the state of warm dense matter. So we will perform some measurement where the density is quite high, so something of the order of 10 to 21, 22 per centimeter cube. Then the proton beams that pass the plasma here will be collected by a set of quadruples that will be developed at INFR that have the role to focus the beam and to improve the statistics in our detector. And then here we will put some detector like a magnetic spectrometer or time of flight like the diamond or silicon carbide that are developed inside. Sorry for the characters, something changed with the conversion of the PowerPoint. And the same, in parallel, we will perform an experiment at INFN, because at INFN we have the possibility to have a plasma from a capillary discharge. So we have a capillary where we put, in this case, hydrogen gas, sorry. then we will perform the discharge, and we have proton source in the range between 10 and 50, 60 kV. So this part of the experiment will be performed shooting, let's say, 40 kV protons in 2 centimeter of plasma with the density of 10 to 18. And the particle will be detected with the dipole spectrometer and a matrix of diamond that will be developed inside the project. So this is a complementary measure that we will perform in our laboratory with a much more stable plasma, let's say, because the plasma is much more stable. This plasma duration is something of the order of 1 microsecond, maximum 2 microseconds, but in 2 microseconds we are able to measure the energy loss of ion, well-controlled ion that will pass through the capillary and through the plasma. And this will serve also this with for benchmark of the jump for models that we are developing. And we should thank Dieter for the useful discussion that we are doing indeed in this field. We had and we will do, I hope, also in the future. So what we did up to now in this field, just a few words, and I finish my talk. So this is what we are doing inside Jump4. Basically, we are developing, integrating stopping power model inside Jump4. This is a complementary activity, very important for us. We choose the modified Lie-Patrasso model. And we are inserting this inside the Jump4 standard electromagnetic physics. So we are creating a custom class derived by G4B electromagnetic model and plug it inside the G4B energy loss process. So basically, for the moment, we are working with hot, very dense plasma, so something that is with an energy around or greater than 200 kV and density between 10 and 100 gram per centimeter cube. But we are working also, we saw that this same model worked well also for a lower density, but we are working on this. So we are starting. I don't want to tell you the details on Jump4 and development that we are doing, but we are working on this topic. And this is how the G4 plasma class are inserted and the interface that we are developing inside Jump4. So these are the base class of Jump4, and we are developing this G4 plasma layer that can read the different stopping power table to model the plasma inside Jump4. And we have this G4 plasma roadmap that will be published very, very soon. Well, this is for example, some results of the first, let's say, software verification. It's not a benchmark. So these are not experimental data. These are data taken by the comparison between Jump4 results of stopping power in different condition of plasma condition, stopping power with the modified Lie-Patrasso model with a very good relative difference. So the first implementation are good. And this is this data and this algorithm and Yeah. Yeah. Tutto The energy selector in principle can be used also for carbon. To be honest, I don't know which are the, because we did simulation, but I don't know which are the characteristics of the carbon, but in principle, yes. It's,
Okay. And another very short question or comments. You make a very good progress on the G4 plasma. And is it also considered the plasma density effect so that it will
for the moment,
have some field? Yeah. No. And then I think maybe do the G4 for plasma for this kind of targeted design will be very useful. Yeah.
it will be very useful. What we are doing now is to use a very simple situation. We have no time dependence, no plasma effect, particular plasma effect, just an homogeneous plasma. And we are testing with this homogeneous plasma, we are testing the model inside the code, and we are see which are the range in terms of density that are good and I mean, one of the problem is to have experimental data because we don't have data to make the benchmark. In principle, with Jam4, we can insert also time and also some different effect. You can do basically what you wish. It's a question of manpower and time. So for this reason, I'm trying to push people together. And if there are people that want to collaborate with this G4 Plasma idea, we can do this inside the Jam4 collaboration.
Yeah, well, maybe.
And
looking forward.
Yes, yes. I think that is a very, I mean, it's very important to try to have an effort inside the collaboration because what I want to do is that we are proposing this inside to be published inside the Jam4 release. I mean, yeah,
Okay,
it's a work ongoing.
Thank you. Looking forward.
Please, last question. Sorry.
Yes. Thank you, Carlo, for this extensive presentation of your portfolio of activities. I have a question still on this, on the measurement of value stopping in warm dense matter. It's a very challenging measurement. I wish you succeed. I mean, it's very challenging, not only for the aspect that Peter has brought up, but there is another one which is also more or less linked and concerned the statistics of the measurement, because I mean how to take energy struggling into account in this case. I mean, because that's part of the statistical variation of the average energy loss, and making a good statistics with this experimental configuration might turn out to be a formidable endeavor. Also because you have to take into account not only the inherent statistical variation of the tone energy loss, but also the inherent statistical variation of your plasma state. So you have to shoot quite a lot. I mean, there and
yes,
with this setup, every shot, I mean, is an endeavor by itself.
I agree. You know, this will be an high repetition rate laser. You know, in the paper, this is basically will be an evolution of the work that was published by Malcolm. And the novelty for these are these three quadruples. So what we saw during the first experiment is, as you say, that we have a loss of a particle here. So the reason why we are developing these three quadruples is to collect more beam in order to have more statistics on the detector. So the improvement, one of the improvement in this direction is the use of this triplet that will focus more and we collect more particles. Yeah, we will see. I mean, I know it's a challenging experiment, and we hope to succeed. I don't know what to say.
Okay, thank you. Just due to the time limit, so we have to move on. So thank you. And next speaker is Professor Xiguang Cao. He will give a talk study on joint charge particle and prompt Gamma-ray dual channel diagnostic scheme for the user.
Okay. Good morning, everyone. I'm Xi Gongchao from Shanghai Advanced Research Institute, Chinese Academy of Sciences. Since it's my first time to this symposium, let me first thank the organizer to provide me this nice opportunity to have a talk here. As we know, have accurate and reliable diagnosis is still challenging in the PB fusion. In order to address this challenge, as I support a proposal to the EN fusion program committee. Yeah, my talk is based on the proposal I submitted. It's a methodological research. My talk has several parts. First, I briefly introduce the background. Then I briefly show the joint dual-channel diagnostic scheme, and also then following my research foundation and also innovation scheme of this proposal. Finally, I give an implementation of the schedule and a short summary. The cluster show up at every scale in physics from the nuclear structure. It is very common in the latin nuclei to the galaxy. The most striking point is that the origin of the carbon-based life and also the nuclear synthesis, it all show up in the cluster structure. Actually, we can show without the cluster structure, we can't be here. So the origin of the carbon-based life and the future of the human maybe is related deeply in the cluster structure in nuclear physics. In the proton-boron fusion, it long envisioned as the ideal energy source. From the nuclear physics viewpoint, its cross-section, decay path, and decay dynamics are all closely linked with the nuclear cluster structure. For example, the alpha 1, alpha 0 decay by the ground state of the barium 8, and alpha 1 it's from the excited states. The fusion proceeds through the several excited states. I think this states also very close with the the cluster structure or molecular structure. This here I just briefly introduce my research background. I'm focused on the nuclear structure for many years, based on the domestic and international large-scale facility. In my group, we have built a full chain innovation pipeline from the nuclear theory study to the advanced detector array development. Also, we developed the intelligent data discrimination method. Based on this study, we extended our research to the national strategic cross-disciplinary application, including the fusion. Actually, involved in some fusion program many years ago, but did not really don't have chance to many contribution. Also medical isotope and also the using the petrol laser to accelerate the new kind of beam. Let's zoom out to the global picture. This is the landscape it can be divided into four halves. There are many research activity and facility around the world. I'm very sorry for the mission. In the North American, the TAE technologies and also the PPE fusion. In Europe, the pro bono funded work of more than 40 countries, also the Marvel fusion. Yeah. In Asia, now here our host of the symposium, the Lean Group, they have the EXL 50 facility. They already makes breakthrough, have first realized the 1 megaampere discharge last year. Also, there's many laser driven fusion research in China based on large-scale facility. Also, the NFS in Japan. In Australia, the AB11 energy. It's a laser-driven fast ignition. They push this approach. Yeah. If we look across the different facility and method, the diagnosis is, I think, is still missing. Yeah. So there is a gap. I think research gap. For example, most of the study focuses on the single channel diagnosis. So we propose to use the dual channel alpha gamma Bayesian framework to address this gap. I think there are several core challenges in this diagnosis. The first one is the peak reaction cross-section is very small, only 1.2 bar. The PB cross-section is not a single smooth resonance, but a multi-peak structure compared with the DT fusion. Also, the very big challenge is the calibration of the geometry efficiency is very high challenge, depending on the transport of alpha in the tokamak, and also how the geometry and magnetic field affect them. Yeah, there is also a very strong gamma ray background. Even with low gamma alpha ratio, the gamma ray may come from the neutron captured gamma or Proton gamma. So why we want to use the dual channel, as the single channel alpha only or gamma only is hard to separate the reaction rate from air temperature. Yeah, the alpha and the gamma channel, they respond to the plastic condition through different mechanisms. So combining both, they can give us two independent constraints to solve R and temperature simultaneously. So we propose to process through the Bayesian framework. So we want to turn them into a two ambiguous partial measurement into one constraint result. It's the first part of my scheme. First, we need to accurate input at the parametric alpha source modeling. In the analytical formula in this paper by Dimitri, yeah, we can get a very smooth alpha energy distribution. Additionally, we want to extend the angular distribution, to get a smooth distribution from mathematically way. So this alpha source is the starting point of the entire simulation chain. Yeah. Then the second one I want to show is we need a think on the particle fix. Yeah, the products of fragments is too many kinds. Yeah, the charge and the mass number is very near. So the analysis is very time consuming and also heavily rely on the experience. Also, is have poor repeatability. So we propose the machine learning to do this PID. This is the first successful application of the intelligent algorithm to address the PID problem in this energy region. Our group also have rich simulation experience, including we built a full gentle simulation for the detector contraction and to guide our experiment. This simulation is all validated and verified. Yeah. We also carried out the PIC simulation for new kind of beam using the parameter of petawatt laser in Shanghai for the head-on and gamma and the positron acceleration. Yeah. I think this is I just very briefly show the innovation of the schedule. We unified the alpha and gamma dual channel diagnostic framework with a full chain progressive technical routine from the nuclear radiation modeling to the experimental validating. It's a cross-domain methodological transplantation. We want to push out advance the relative dual channel diagnostic work, and maybe it can help to advance the realization of this routine. Here is I divided our schedule into four parts from phase 1 to phase 4. Here is a very brief summary. I think the dual channel diagnostic is essential in proton-boron fusion, and the digital twin simulation study for the dual channel diagnostic are necessary before the system is really implemented. The experience and techniques developed in nuclear physics can help support the diagnostic research on proton-boron fusion. This is the reference. Many thanks to my collaborator teams. Thanks for your attention.
Thanks. Open for question. Any question? I have one. You choose a dual channel and to apply for the PB fusion.
Yeah.
What kind of problem you want to solve? Try some new state like cluster or just use this reaction?
We want to diagnose the parameter state and how the reaction rate or temperature are in the PB fusion. We want to probe the state. Since the RO only the alpha or gamma is very limited in the diagnostic schedule now. We want to use both information. Since gamma carry out the very directly information, but also but the alpha is very low ratio.
Okay. Another question, because this PB fusion will happen in this spherical torus. Probably in the center of just outside of the shell. And then you have, in your scale, do you have any special resolution? Because this probably happened here. The pathway, the energy will decrease of alpha, so you can separate this from where.
You are right. You are right. We want to implement the simulation, the full simulation. We call the twin, digital twin simulation to simulate all the electric details. From counterpart to the detector.
Okay, thank you. Any question more? If no, okay, thanks, speaker again. The third one is Miss Liu Yuxiao. She will give us talk about research on alpha detection of hydrogen-boron reaction based on silicon cobalt detector.
Good morning, everyone. I'm Su Yuxiao from Shandong Institute of Advanced Technology. Today, I'm really happy to be here sharing my recent work, research on alpha detection of proton-boron fusion based on silicon carbide detector.
I think we can start. You remember some words. Okay. So good morning. I think we can start this second session of the morning. And in this second session, we have 4 talks. The talk will be 20 minutes each. So I ask to the speaker to stay in time, and I will tell to the speaker 5 minutes in advance when they have to 5 minutes in advance of the end of the talk. So we can start with the first talk, and I wish to invite Anton Moroz from University of Bordeaux. He will discuss the talk on the experimental characterization of laser-driven proton acceleration with the near critical foam target. So you know, foam targets are very interesting in our field, as they show a very good energy absorption, energy conversion. So it's useful for particle acceleration with laser-driven, but also for fusion application in general. So thank you for the talk, and I will tell you 5 minutes in advance.
Hello, everyone, and thank you for having me here. So, as you see, I present a pretty big collaboration of people, and you can notice that ENN is here and Peking University is here. So we really are partnering together to have this experiment. Laser acceleration is of large interest because it can create teravolt per meter electric fields. So it's really a very high, very compact mechanism. And yesterday we heard about Coulomb explosion, but probably the most commonly used mechanism is target normal sheath acceleration, where the laser interacts with a solid foil, usually several microns thick, and it accelerates electrons to relativistic energies, but ions, because they're very heavy, they stay in place. They don't have enough time to react. And so the electrons transverse the foil and accumulate on the back surface, which then this field ionizes just a couple of layers of contamination on the foil surface, and then accelerates these ions along the target normal direction. And then the electrons recirculate inside the target, and some acceleration in the opposite direction also occurs. And so these solid foil targets have a large disadvantage, even though they provide very controlled and predictable beams, but the density leads to laser reflection from the target surface. So in fact, only a couple percent of laser energy is coupled into the accelerating ions. But if we can manufacture the near critical density targets, the critical density is defined by the laser parameters. We can, in fact, make some foam with a mass density lower than critical. And so the laser can penetrate inside the target and interact not only with the surface, but with target volume. And this will lead to enhanced energy coupling into the ions. And so our goal for this experiment is to characterize 3 types of targets: the common foils, some foam targets, and the combined configuration where we have a foam backed by a foil. This experiment was performed in Felix laser in Darmstadt, and we used 57 to 80 joules of energy in a high contrast mode for some shots with 600 femtoseconds, and with also by adding a nanosecond ionizing pulse before the main pulse, with different delays of 3 or 5 nanoseconds before the main pulse. For the targets, we used 13 micron titanium foils to have a benchmark for classic mechanism, and 500 micron 2 milligram per centimeter cubed foams manufactured in Myanmar. They are carbon-based foams, triacetate. You can see their structure here, and well, the combination of the same foam backed by the same foil that we use in the first case. And we also had some very thick foams, 1 to 2 millimeter thickness, manufactured in Australia. And the mass density is very close, where the critical density for these laser parameters is about 3 milligram. So it's really near critical, but the laser still can penetrate. And for diagnostics, they all were placed around the primary target. The laser was at 15 degrees to target normal. And so in the front direction, we had radiochromic films, Thomson parabola and magnetic spectrometer, which were able to characterize the main emission cone for the protons and other ions, light ions. And then we had a possibility to look at asymmetry of the acceleration by comparing two magnetic spectrometers, which were placed around the same angle from the target normal. And then at lateral directions, we mainly had just relative diagnostics to compare particle yields and cutoff energies. We also had a boron nitride sample placed for each shot to measure proton-boron reactions, but mostly proton-boron 10, of course. And then we tried to measure alpha particle emission from this boron nitride with CR39 detectors. And finally, we had an X-ray spatial resolution spectrometer to look at titanium plasma lines. Radiochromic film turned out to be probably the most informative diagnostic in this case, because we were able to see the full beam profile at different energy and really see its evolution throughout the energy range. Based on some work by Schmitz, we developed our own processing code that is automatic, so it eliminates human error. And basically, it segments the beam from the background, then converts it to dose using absolute calibration, which was made with X-rays, and then well, determines the beam size. And then we can reconstruct the proton spectrum from these RCF layers based on two independent methods. First of all, which is deconvolution based on proton energy deposition in the active RCF layers. And the second method is a convolution with an exponential function, which also uses a response matrix to find the best, well, the best fit with this function. And as you can see here, with the blue dots and the black line, well, in some cases they agree better, but it shows us the possible error source. And so you can see here the pictures for the three target types. So the foil is here, is the standard picture where we have a defined beam, which decreases in size with energy. The foam targets, the first layer is completely covered, and it shows very high divergence of protons mostly, and other ions too. And the cutoff energy is low. And then foam plus foil target, you see much more RCF layers are irradiated. But you can notice something that we noticed that actually we see two beams, and one of them follows target normal direction, and the second one follows the laser direction. And so it is a known phenomenon which is caused by a plasma channel that focuses an electron beam, and so it remains very well defined, and it penetrates the target and just escapes. And so this is a sign of really enhanced electron generation and also electron focusing in specifically this target configuration. So here you can see some average spectra from several shots. The foil here has the medium cutoff energy, but it also had the lowest emission half angle. But then the foam targets, they have more protons in low energy range, but a very low cutoff and high divergence, which we have to extrapolate because the full RCF is covered. And then, the maximum energy is almost 2 times lower than for the foils. And the foam plus foil configuration, here we have to mention that usually it was used with a pre-ionizing pulse to ionize the foam layer, but keep the foil untouched. And so it produced much higher energies, although you can see large variance between the shots. And so the energy was 40 megaelectron volt at much lower laser energy compared to the foil. And the spectrum really just shifted towards the higher energy region because the amount of low energy protons decreased. Overall, we observe about 76% more protons in the range above 15 megaelectron volts. Then we can look at the difference between front and rear target normals. And this really more depends on the laser shape than the target, because we see that both for the foil and foam, where we have a high contrast shot, the cutoff energies are comparable, which means that the accelerating field magnitude is comparable between forward and backward directions. But when we use the pre-ionization with the foam, there is a very large difference, which basically means that plasma expansion from the foam towards the laser decreases the density gradient, and the acceleration in the backward direction becomes not effective. But in the forward direction, this pre-plasma actually enhances the acceleration. And so here you can see the cutoff energies at all different angles, and it becomes even more clear for the green line is the foam plus foil combined target, where we have a very high cutoff at 0 degrees, so the rear normal, and a very low cutoff in the different normal direction. And we also had these thick foams which were highly ionized, and this basically produced a very uniform field, basically spherical, which is not effective, but it is almost the same in all directions. So we have some activation results, but it was challenging because of different placements of activation samples, and there was probably not enough stability to make good conclusions. But we do measure beryllium-7 in many shots with with all target types, but we did not measure any alpha particles at CR39, and basically there are two reasons. One is that the CR39 were very far away from the sample, but also the sample itself was probably not large enough. So we do not measure alpha particles here. we observed also some interesting thing on the RCFs. It's called a ring-like structure for the lowest energy protons. And this occurs only at high laser contrast, and it is also known in literature. This structure, so you see the maximum of the proton flux is in a ring around the center of the beam. And this is caused by a transversal accelerating field. You can notice that it is really the same between the foil and the foam plus foil targets. And this means that this transversal field is only caused by the foil layer, and that this foil layer, at least for this field, is in the same conditions between the different, between the both targets, because the opening angle is exactly the same in these cases. For the X-ray spectra, we indeed confirm the high laser conversion in foam targets. So we measured the electron temperature about 900 electron volt and the density 4 to 10 to 20. For the foil, if you look at the red line, you see high K alpha and helium alpha emission, which means that, well, this shows how the spectrum looks where the laser just interacts with the foil. So it's just heating of the foil with the laser. And for foam and foil configurations, we see different results because some shots do have this strong helium alpha line, but some of them don't have it at all, which means that in some shots, the laser can reach through the foam and hit the foil, and in other shots, it cannot. And where the laser does not reach the foil, we actually see even more effective acceleration, which means that more of the laser energy is transferred to the plasma. And also worth to notice that with very thick foams and pre-ionization, we still do see good electron conversion, although we still see good laser conversion, although the protons are not effectively accelerated because this field is distributed along the large volume. So basically here is the insight into the physics of what is happening. In all near critical density foams, the hot electron generation is enhanced since the laser can interact with target volume instead of just the surface. But in ionized foam plus foil targets, the foil layer here, it serves as a barrier, so it prevents plasma expansion along this direction, and it preserves the density gradient. But also it protects the foil from destruction by the ionizing pulse. And so we do see some plasma channel being formed along the laser direction, and we see very effective acceleration in target normal direction. And the cold foams without pre-ionization, we do see enhanced hot electron generation, but because the foam is solid, they scatter to a large focal spot, to a large spot on the other side of the target, and produce a very highly divergent beams with decreased magnitude of the accelerating field. And we also did have some shots on this foam without the foil with ionization, and there we didn't see any effective acceleration because the field just the plasma just expanded in all directions, and there was no sharp accelerating gradient. And yeah, so this happens both in foam, thick or thin foams. So, in conclusion, we confirm that near critical density targets enhance laser ion acceleration compared to conventional foils, and TNSA still remains the acceleration mechanism. Proton source spectra and angular distributions can be tuned by selecting different target configurations and more
Yeah, I- is
Oh,
Uh, sure.
the the is
And it's
I we
department of the proton-boron fusion near the temperature of 100 eV. So we want to know is, can this strong screening mechanism be used to enhance the reaction rate in such kind of magnetically confined fusion reactors? In order to answer these two questions, my talk will be divided into two parts. Let's first start from the very simple cases. We call it isolated atoms. Basically, the screening potential is some kind of a response of the electron around the nuclei to the incoming projectile. So in this case, we can calculate it using the density functional theory method. In this method, the total energy is a function of the electron density. And the electron density could be calculated from this wave function. And this function is controlled by the so-called Cohen-Sham equations. In these functions, the most important thing is the potential. So this is the external potential, and this is the Hartree term, and this is exchange correlation term. The gray one and the red one is very important because the Hartree-Fock energy describes the classic electron repulsion. It is will give us a stronger screening, and we put other effects such as the quantum effects into the exchange correlation energy. These functions should be solved. We call it a self-consistent method because you know they coupled together. Okay. Fortunately, we have they have a lot of DFT code has been developed. I want to introduce two methods we used in this work. One is called Abnett, which is based on the pseudo-potential method. In this method, the inner core electrons is frozen, so its response is could be cannot give accurate response of the inner electrons. Another kind of is a Python-based simulation of the chemical framework. In this software, all electrons could be relaxed, so it's more accurate for in this work. We define a total energy. This could be derived directly from the software, and the potential could be obtained from the HB system and the minus a reference. The reference means the H proton atoms, and the distance between proton atoms and the boron is much larger. To their interaction could be the calculation, but in the region very near to the nuclear surface, the Fermi Dirac gives a step, a small hair steps. Used this, according to this model, he studied the proton-boron reaction near a golden nuclear surface, where the density of the electron is in this case. And the calculation showed that nearly or strong local, almost temperature dependent screening effect was observed. We can say it is about 14 keV. And this is for proton-boron reaction, and the DT-DD and the D-helium-3 reaction was also calculated to get the reaction rate enhancement. We can find for the proton-boron reaction, the local microspark enhancement can reach about 1.5 at the temperature about larger than 100 keV. So I think this is a small summary. Grayson's formalism described a different screening regime near nuclear surface. In the nuclear surface where the local field is strong, linear, the relativistic Fermi Dirac statistics are used, which is better than which will give a good accurate correction to the debate model. Another thing is in such kind of his framework will be used in that case. In this case, in laser-driven inertial confinement, where hazy nanoparticles are induced, local strong screening will enhance the light ion reactions. This is the conclusion for our for my talk. The diabatic atomic contribution to proton-boron screening is limited to about 350 eV. In the static crystal environment, the correction is small. So we can see the recommended screening potential is around 350 eV in solid environment. Moreover, this is a comment from to the Grayson's work. Moreover, while introducing heavy impurities may enhance local screening, but the associated very strong long losses will far outweigh any reaction gain, limiting its practical applicability. So my conclusion is that this framework from the self-consistent strong screening by heavy ions cannot be used in our proton-boron magnetically confined reactors. So thank you. And
Thank you, Mr. Professor Sterling. Time. We are 10 minutes late indeed, so it's time for one question.
Very good research. I have a question. So you now consider the potential typically from local
yes,
atomic is not come from the environment. You say the environment is not so important compared to the local screening potential. So, but my question is, when we consider the ICF or we the density there is not local. Maybe it's about plasma environment. It is very high density. So I'm thinking, do you have any idea on this topic? Maybe a little different to your work now.
In my opinion, the screen, yes, you are right. For the solid target environment, in the proton-boron, in the boron solid target, the screening mainly comes from the local, the isolated electrons, isolated atoms, not from the heavy ion. But in this laser-driven internal confinement, if we could induce, for example, if we could induce some heavy ion impurities, such as good atoms,
Also local.
Yes.
But my question is the compression already create a very high high density environment.
Oh, okay.
A positive of compared to a solid density.
Or this enhancement could only happen near the heaven air.
Oh, so
Cannot happen. We cannot find such enhancement far away from the heaven airs.
yeah, but in PP, we also care a lot on the lengthiness state. But it seems to be you just shift a little the energy of the measurement energy, maybe in your case. So,
Yes.
okay. Thank you.
I have to interrupt. We can continue later. Thank you very much. Thanks again to the speaker. Interesting talk, and we can move to the last talk of this morning, for simulation and detector response study of the low energy proton reaction from Xin Han.
Yeah.
From Shandong University.
Yeah.
Thank you very much for
Thank you.
listening to talk. I will tell you 5 minutes.
Okay. Good morning, everyone. I'm very happy to have this opportunity here to introduce my work. It's about the GenFlow framework for the proton-boron reaction. I will focus on how the different reaction channels are modeled and what the simulations tell us about the detector design. Here, this work has 3 parts. First, we built the physics input for proton-boron reactions, including the reaction channels, cross-section, angular distribution, and angular correlations. And second, we put these models into GenFlow, which transport the particles through the target and detector geometry. And third, we study the detector response. We ask which observers can separate the decay channels and how the detector coverage and resolution affects the results. And next, let's talk about the reaction channels for this fusion. Here there are 2 important resonance in this energy range of interest. The lower one is the 162 keV in proton lab energy. It forms the 2+ state in carbon-12. And the higher one is the 675 keV and form the 2- state. These states mainly decay into the 3 alpha particles. The decay can be sequential. Carbon-12 first emits 1 alpha particles and leaves the beryllium-8 either in its ground state and in its broader 2+ state. And the beryllium-8 then breaks into 2 more alpha particles. And for the 2- state, the decay to the ground state is forbidden. And also, a direct 3 alpha decay is also possible, and the gamma decay branches are very small but also included. And for GenFlow, we need the total cross-section, the angular distribution of the primary alpha, and the angular correlation of the secondary alphas. And here, let's talk about the kinematics. The event generator uses the Foley relativity 4 vectors. We first calculate the invariant mass of proton-boron system. Then we take the first 2 body split in the center of mass frame. For a sequential event, the products are the primary alpha and the beryllium system. The mass of beryllium is sampled event by event for the required line shape. And next, we choose the direction of the primary alpha from the physical model and boosts the particle into the lab frame. And the second decay point, beryllium-8 breaks into 2 alphas in its own rest frame. These particles are then boosted back to the lab. And also the direct channel uses the same general pipeline, but the final state come from the 3-body phase space. And as a check, the alpha 0 events follow the exact 2-body curve. This shows that the kinematics and the Lorentz-Bruce are correctly. And then let's talk about the 162 keV resonance. First, it's about the cross-section. It's described by a single-level Britt-Wigner form. And the proton weight changes with the energy because the proton mass passes through the column barrier. Since the entrance channel is a p-wave, this energy dependence is strong. And here, the green curve gives the model, and the points are the experimental data. And the model reproduces the resonance position and the strong separation on the low energy side. And in the simulation, this line shape is used to sample the reaction energy across the beam energy distribution. And here we talk about the primary alpha in this resonance. And the primary alpha can fit into the 2 beryllium-8 states. The alpha 0 channel fits the ground state, while the alpha 1 channel fits to the broader 2+ state. And the angular distribution is built from a coherent sum of partial waves. We first add the amplitude. We first add the amplitude and then take the absolute square, so the interface terms are kept. After the weakness 3J recoupling, the result is written as a legendary series, which can be sampled directly in the Gen 4. And the two plots on the right show the physical result. And for alpha 0, both final fragments have the spin 0 to conserve the total spin of 2. The relative optical angular momentum must be L equals 2. This gives a symmetry cut clearly anisotropic distribution with large yield near the 0 and 108 degrees and the minimum near the 90 degrees. And for alpha 1, the beryllium state already has the spin 2, so the L equals 0 is allowed and dominates. And an S wave has no preferred direction, so the distribution is nearly flat. So here we can see the spectrum. And at this plot, the red line is the energy in the center of mass of the mass frame, and the green line is the energy in the lab frame. And for alpha 0, the center of mass energy is almost fixed because it decays to the very narrow beryllium ground state. And this is why this red line is a sharp peak. And in the lab frame, the energy also depends on the emission angle, so the green line splits widely. And for alpha 1, the red distribution is already broader because the beryllium 2 plus state has a weight of about 1.5 MeV. And the right plot and this plot confirms the angular behavior. Alpha 0 is anisotropic, and while alpha 1 is close isotopic. And then let's look at the secondary alpha particles. And here, the alpha 1 channel dominates the yield and gives a very broad energy spectrum, while the alpha 0 channel gives a much narrow low energy group. And these angular correlations are also different. For the beryllium ground state, which has the spin 0, the breakup is isotopic in its rest frame. And for the 2 plus state, the population of the magnetic substates carries the alignment from the first decay step. This produced clearly structure in the angle between the secondary alpha and the primary alpha direction. So in this figure, the primary alpha may look almost isotopic, while the secondary alpha correlation still keeps strong information about the for the pressure the in silicon geometry and qualify its triple alpha efficiency channel separation capability. And we also want to fit the dice distribution to try to extract the angular distribution parameters. And also we can, in this framework, we also can use the polarized beam or the polarized target to see what happens to the measurements. And thank you, that's all.
Thank you very much. Very good part. So I have one question. I noticed in the very beginning, you assume P wave,
Yeah.
but at very low energy, normally it should be zero. S wave is more important. So how about S wave in your simulation?
It's according to the so about the S wave, P wave, or D wave is according to the angular momentum. So it's about which state they populated, I think.
You calculate I mean, the P wave is between angular momentum between proton and the boron, right?
There is and Proton-Boron. Yeah.
Calculate if the energy is very low. P waves should be very small.
Okay. Thank you.
Yes, under slide 13. So are you saying here that your model agrees basically with a lower total cross-section for the main resonance and was previously reported?
Sorry, I didn't get.
I'm saying, so your model curve is the blue curve?
The blue is the model.
Yeah, the model is the blue curve. Yeah.
Okay. So is I mean, most of us have been using the cross sections from 2015, 2016, and so on. So you're saying that the cross sections, if you agree with a good deal lower. This would be a correction of about 1/3 the total cross section.
Yes, I noticed. Yeah, and this is for the simulation. So I want to use the same method just like the resonance before at 162 keV. So there may be some parameters it's not very well known. So makes this this curve is lower than the experimental. Yeah.
Okay. Thank you.
I have one comment, one question. You know that you inserted this model inside a Geometry simulation.
Yeah.
So you change the cross section of the table cross section, or you are importing one new models. I not catch this point. For the final distribution of your
the total cross section are used.
But we change the total.
Yeah.
Okay.
Yeah, and the angular distribution is from something here or something here, we can get the angular distribution. Yeah.
And you are thinking to insert this inside the Jump4 or not? You spoke with the Jump4 collaborators for the collaboration.
No.
Okay. If you have this idea, in case you can discuss.
Okay. Thank
Okay,
you.
so thank you very much. You can go to lunch.
Yeah. 我们有没有人？
The lunch is still on the first floor, and the afternoon session will start at 2 p.m. Please be here on time.
哎，我们这样要上这个。下回的报告怎么发给用的？我是个，
我有一个
没有约的。对对对，不是这个咱们那个。你现宣布什么？现在宣布是
They for a while will take some.
I think there is an announcement here. Help us with the chairs to the front, 前面。还有我们自己的人放哪去了？给你一个啦。来帮忙帮我们去。做补工。
就是这个 V2 的这个。
待会儿留下来给我们刚刚那个。
这个是吧？
这是我实心。
外国的专家们一个。
啊，好，来，我先看一下测试。
来，我们请潇潇大力士放翻译的。几把？
第三个。
那个其中我们一共有多少人啊？然后再加上尽量搬，多搬几个，潇潇不要管。你搬了再说。年轻力壮的搬一站。这个是。
这个 video 可以放。
哪个？这个上。
不是这个 video。这个。您试一下。
您试一下。
对。我要不先暂停共享吧，现在在共享。
这个没有关系的，因为我们是直播，直播那边直接就会关了的。
哦，行，那我在这儿，在这个电脑对一下就行。
这个反应啊。
好，你得放映了才行，放映了对。
哦，行，那我就在这放映吧。
对，因为你放映了得看那个大屏上有。
哦，对，那试一下。
来，继续看。
怎么点？